We've talked before about the need for a soft iron core in our transformers, and I thought I would show you why the soft is important. So let's start with a hard magnetic material. Here we have a piece of steel, maybe, inside our coil of wire, and I'm going to apply a magnetic field to the piece of steel by passing current through the coil. So there we have a large positive current, and you can see that we have reached a magnetic saturation, in the sense we cannot make this magnet any more magnetized than it is already. So if we then reverse, so we're now demagnetizing and remagnetizing the other way, you can see that we didn't follow the same path. Now let's remagnetize the way we did the first time. You see we have this loop. We came up here, we came back along here, and then when we went back to our original magnetization, we followed this path. So in here, this space represents lost energy, energy that has been stored in the disarray of the magnetic dipoles. So this loop is called a hysteresis loop, and it represents how much energy is being lost. We have a similar sort of thing with old rechargeable batteries, for example, nickel metal hydride batteries. So, or nickel cadmium batteries. If we then go to the opposite extreme, we have a soft magnetic material, that is to say easily magnetized and demagnetized. And let's do the same thing. You can see that comparing that to our hard magnetic material, notice how much more magnetized our soft magnetic material became. Notice we are about halfway between these two lines here, and if we go that way and apply the same strength and magnetic field, see how much more magnetized our soft iron becomes. It is easier to flip those little atomic magnets and make them all line up. If we then reverse the field and back again, you see that we are very much following the same path. That's not exactly the same path. You can see the line has got thicker, so we haven't quite followed the same path. We're reaching the same level of saturation, but it's not quite the same path. There is still a hysteresis loop in here, but it's much, much smaller than with the hard magnetic material. So this is a material that once it becomes magnetized, although it is more difficult to magnetize it in the first place, once it becomes magnetized, it doesn't really easily demagnetize. It takes a lot of energy. So you can see we have a much bigger hysteresis loop here, much more energy lost in the cycle of magnetizing and demagnetizing compared to our soft iron core. And remember, what you're doing in your transformer is you're putting your soft iron core into a changing magnetic field. So this rather gentle, slow process that we are exhibiting here, the field is going from 0 to a positive maximum to 0 to a negative maximum to 0, 50 times a second with mains. So this change of field is happening a lot. Now if we did that with our hard magnetic material, look at the energy losses. And of course, we want the soft iron core in there so that we add its magnetic field to the field around the primary coil. So there is a stronger magnetic field going through the secondary, which means there is a bigger rate of change of the field through the secondary, a bigger change of flux linkage, bigger rate of change of flux linkage through the secondary, and therefore a larger induced voltage potential difference, EMF. So that's what it's there for. And one of the energy losses in a transformer is this hysteresis. You can't get rid of it entirely, but you can minimize it.